Okay, class, we're looking at neurology still, and this is always a fun slide to go over because um, it shows what's called hemispheric lateralization. Whenever you hear the expression, oh, he or she is left brained, or I'm more of a right brained individual, let's look at what people are really implying by that. So, when we look at the left hemisphere, when I think of left, I think of the letter L and everything that deals with L, like language, I think of logic, I think of linear thinking with numbers and science, um, logic, which is reasoning and rationale. So that's more left brain, more of the math, science, linear, logical, rationalization brain. Whereas the right side is more artistic awareness, more like musical talents, and being able to determine if this shirt goes with these pants, if this tie goes with the shirt. Should I put the couch on this wall? Should I put this picture over there? Right? That type of spatial pattern awareness and perception is right brain. Being able to, when you're a baby and you come into the world, you have to be able to have a familiarity and be able to look at who the parents are, who's mom, who's dad. There's this understanding of facial expressions and being able as a baby to differentiate a smile versus a frown. And that's why babies sometimes misinterpret a smile and then they start crying because they see teeth and they think teeth is anger, right? Like an animal showing its teeth. So that right brain is more of like your art, your music, your spatial and pattern awareness, facial recognition, but also the emotional content to communication. Where notice when I teach, I always use a sort of affect in my voice to try and capture the people who I'm speaking with compared to me teaching like this in a very linear, robotic way, I would not be able to capture your attention very long. You would be bored by my ability to teach you, right? That's more left brain. And there are people that do communicate that way. Either they communicate that way because they're left brain dominant or right brain damage and it's not allowing it to express itself. So in healthy individuals, we should be able to communicate back and forth, right? I mean, you've got this corpus callosum, so you can be able to do some science and do some math and be able to rationalize and be able to enjoy some music and be able to have a little bit of both left and right brain. Okay. Um, Now, there are people that tend to be more left brain dominant and people that are more right brain dominant, but the more you use that part of the brain, the stronger and more developed it becomes due to neuroplasticity. Okay. Females biologically have a larger and stronger connection between these two sides. That is referring to the corpus callosum. And again, when there's damage primarily to the left side of the brain, that's when aphasia kicks in. Damage to the same area on the right side produces speech with little emotional inflection, more of a robotic type of speech. Okay. When we come into the world, we are right brain dominant. And then over time, the left brain kicks in and we try and balance them out. So, left hemisphere, left brain, mostly reading, writing, math, science, decision making, speech and language, mostly left side. And your right side, remember, is more of the music, art, dealing with your senses, really good intuition, recognition of faces and voice inflection, primarily right side. Now, what I wanted to show you here, the reason why I like this picture is a few reasons. Number one, when you look at the left hemisphere, you see that it controls the right hand. And when you look at the right hemisphere, you see that it controls the left hand. But the other thing that I want to point out here is when you look at the eyes in the cerebrum, there's cranial nerve 1 and cranial nerve 2 that originate in the cerebrum. One is the olfactory for smell, 2 is the optic for vision. Now, with the eye, we have a temporal field of view, which is what we see here in blue on the right side. And then there's a nasal field of view, which is what we see here in red. Now, when something is in the temporal field out in your periphery, that information hits the receptors on the inside of the eye. When you catch information on this right eye near the nose in the nasal field of view, like right in front of you, that information crosses over to the lateral part of the eye. Okay. What crosses over, right, this temporal field of view crosses over to the opposite side of the brain, and this information on the nasal field stays on the same side of the brain. Okay, so each eye is sending information to the same side of the brain and to the opposite side of the brain. And the neurons, the tracks that go from the eye to the occipital lobe, they crisscross right there, called the optic chiasm, which is just next to the pituitary gland. So when there's pituitary tumors, it can lead to visual deficits. And I'm going to show you this in another picture that's coming up. Just wanted to lay down some foundational work. Right here in the center is the corpus callosum. Those are the white matter that connects both hemispheres together. You can see in the back, that's your primary visual cortex. We have an auditory cortex in that temporal lobe. We could see the speech center over here. Now, in terms of brain waves, when we're looking at electrical activity of the heart, they call that an EKG, an electrocardiogram. When we're looking at electrical conduction of muscles, they call it an electromyelogram. Myo for myology, electromyelogram. When we're talking about brain waves, we call that an electroencephalogram, right? They put these little sensors on different parts of the brain, and they're looking at different waves: an alpha wave, beta wave, theta waves, and delta waves. So when you're at rest and you're just kind of relaxing, we should have these alpha waves present. When you're listening to me teach and you're concentrating, we should see some beta waves present. When you're taking a test and you get stuck on a question and you're feeling a little bit frustrated, we may see some theta waves. And when you're sleeping, we should see some delta waves. This is just another graph of the same alpha, beta, theta, and delta waves. We use these to diagnose people that may have epilepsy, because the brain waves, these are just picking up millions of action potentials that is being created in the cerebrum. So if there's any abnormalities, we could pick that up using an electroencephalogram. And again, the alpha waves are when you're awake, but you're just resting. A beta wave is when there's mental activity, right? When you're concentrating. And the theta waves are present when you're under some sort of distress or emotional stress. And the delta waves should be prominent when the person is sleeping.